In this video, I want to cover a strategy to solve two-sample hypothesis tests. Let's go ahead and look at an example here. A manufacturer of an MP3 player wanted to know whether a 10% reduction in price is enough to increase the sales of this product. To investigate, the owner randomly selected 8 outlets and sold the MP3 players at a reduced price. At 7 randomly selected outlets, the MP3 player was sold at the regular price. Reported below is the number of units sold last month at the sampled outlets. At a 1% significance level, can the manufacturer conclude that the price reduction resulted in an increase of sales? Okay, so keyword there is increase. So did the reduction result in an increase of sales? Let's go ahead and open up the starting file for this solution. Okay, we have our data here. We have the problem stated as well. Let's go ahead and document alpha. Alpha was 0.01%. Let's go ahead and use the format from the table here. Let's indicate what our keyword is. Our keyword was increase, which is going to dictate the direction of our test once we identify our samples. Now, one thing about the samples here, I immediately look and say, hey, there's one less regular than reduced. That's a dead giveaway that we're not talking about a paired test or a situation where the rows actually are paired to some sort of attribute, maybe a person, a room, or a city, or something like that. So we know that there are, this isn't going to be, I should say, a paired situation. So what does this keyword imply to you? The keyword implies to me that we're dealing with a right-tailed test. So increases to the right. Let's go ahead and format that and move on. We already have alphas, so let's go ahead and write the null statement and the alternative statement. Again, I always prefer writing the alternative first. We know that it's going to be a right, so we know that we're comparing a sample here. Sample is greater than another sample. Well, which one is which? Which one should go on the left and which one should go on the right? So we are looking for a price reduction, and if that reduction has resulted in an increase of sales. So we are looking for the reduced price, so let's call that mu reduced. If that mu reduced is resulting in greater sales, so mu regular would be on the right hand side. So this is how I would recommend writing that statement. If we have this statement, we can write the null reduced is less than or equal to regular. Or alternatively, we can write this as H0 mu reduced minus mu regular. And I need to finish that is less than or equal to 0. And it looks like I didn't put mu here, so let me backtrack just a second. Put mu. Okay, so if that is the null, let's write the alternative. H1 is mu reduced. It's greater than minus mu regular is greater than 0. So we can write this either way. I actually prefer the second way. And now we have to conduct the test. Let's go ahead and talk a little bit about that. And let's go to the formula sheet. Okay, once we've identified the right section, the two-sample hypothesis test, we are in fact talking about an increase or a greater than situation. We can check that we have written that statement correctly. And we have the figure here to give us our guide in terms of where the critical regions lie. Let's go ahead and paste that into our spreadsheet. This is obviously optional, but we just want to keep track of the things we're calculating. Okay, so now for the decision tree. Which one of these cases are we really talking about? We only have 4. Are the samples independent? They are in fact independent. If they were dependent, we would have a situation where we were investigating a paired sample. We don't have a paired sample. Okay, so if they are in fact independent, are the population variances known? Well, no, we actually weren't given that at all. So nothing was mentioned about the populations being equal. So we don't know anything about the population variances, and furthermore, we don't know if they are equal. So we are talking about case D. Let's look at what case D is. Case D is this row in the data set, which we can manually calculate all that, but I'm going to use the data analysis toolpack to conduct the research. Look at this table here. Okay, so this decision tree is actually for the Excel data analysis toolpack. If you know it well, you don't necessarily need this decision tree, the second one, but let's go ahead and look at this. Can our 2 samples be paired? We've already determined no. Is the population variance or both samples have greater sample size of 30? Well, no. Is the population variation unknown but is assumed to be equal? It is not assumed to be equal. We are in fact talking about the t-test 2 sample assuming unequal variance. The same thing we led to in the previous decision tree. So we're going to select that test. Let's go back to our Excel file. Let's go to data analysis, and look at the various tests. We are in fact assuming unequal variation. There's only 4 to choose from. If you can roll out a paired, you really only have to make up your mind if population parameters are known or whether the variances are assumed to be equal or not. Most cases it's unequal, but there are cases, of course, where we can assume that they are equal, and if we assume that, we have to explicitly state that in the problem. So 2 sample assuming unequal variation. Let's hit OK. Range 1 will be reduced. Range 2 will be regular, and that's in the order they appear here, so reduced and then regular. Hypothesized difference is 0. We do in fact have labels. Be careful that this is defaulted at 0.5 all the time. We want to change that to 1. And let's put our report here and hit OK. So we are in fact talking about a one-tailed test, so let's auto size the column so we see everything clearly. We can automatically rule out this portion in the table. We don't need that information. It's related to a two-tailed case. The information we do in fact need is the test statistic and the test critical. You can always make your conclusion based on the p-value, but it takes some experience to get used to what this p-value is. 22% to me says that p-value is huge, and your test critical is close to the center. Well, here it's actually, well, I should say your test statistic, not the critical. Your test stat is close to the center at 0.8. So if we were to draw this out, let's go ahead and do that. We would have a distribution that would look like this. We have some sort of center. We're testing the right, so we'd expect positive values for the t-stat and t-critical. The test critical would be somewhere here, and I'll write that as TC. Now, where is our test stat? Our test stat is close to 0. I'll put that here. Of course, if we draw a line straight up, this is our rejection, and the other side is our fail to reject. So let's go ahead and document that. This is the fail to reject. This is the reject region over here. We are in fact to the left of this line, so we are going to fail to reject. Now, fail to reject implies we have to accept, if you will, the null hypothesis. So the mu of reduced is actually less than or equal to mu regular. So we can actually conclude, let's document our conclusion. We will conclude that the reduction has not led to more sales. This is because we failed to reject null. Okay, let's just finish up this with formatting. So again, since we are dealing with a situation where the p-value is really high, and visually I can explain that here. The p-value is always dictated based off the test statistic. So actually, let me draw a line there instead of dotted. Actually, what is happening is the p-value area, of course all probability is an area, the p-value is calculated from this value over to positive infinity. And this p-value is much larger than alpha. So that's how we make our decisions. We look at p-value, compare it to alpha. Alpha in this case was 1%. Our p-value was 22. That means the test statistic is to the left.